I would like to now invite, and I'm going to yield the floor to the chair of the next session, Professor Maria Colliu. She is actually the PI for the collaboration during the first test of the Metropolitan Resilience Project. And she will be chairing the session where you will hear updates on those tests plus some more information. So Maria, are you there?
Yes, thank you very much, Julio.
So you have the floor, and I'll mute myself.
Thank you. So in this session, we'll have presentations from the wood and the concrete test. And the first one would be on the Japan-US collaboration, the wood structure test, and update on the wood test by Professor Takuya Nagai from Nagoya University.
Hi, Maria.
Please go ahead, the floor is yours.
Okay, so I would like to explain wood structure test. Okay. The team was set in the first meeting held in Akasaka, Tokyo in 2017. The team continued preparations for the first test of this project, and this is May of 2018. In autumn in 2018, the construction of 2 test specimens was completed. And in February 2019, the first test was successfully completed. And now, Koryu-san, Maria, your part.
Thank you very much, Nagai-san. So just a very brief update on the US side. You can see the US team members. I was leading the project, and Professor Pandelidis, Professor Ryan, Professor Daschi were co-PIs in the project, and along with collaborators and participants, Professor Barbosa, Vandelate, and Pei. And in the next slide, you can see the 2 students that worked on the project. Mohammed was actually physically in Japan during the test, and Christian Okamoto is an undergraduate student who helped us process data later on. So in the next slide, you will see the instrumentation we used. So except for drones, like Nagai-san mentioned during the construction phase that we used, we also used the 2 LiDARs scanners, the 2 types of LiDAR scanners from the NIERI rapid site to perform different measurements during the testing phase and compare with other traditional instrumentation methods. So we used the long range scanner and the short range scanner. We had the scans in between tests, as well as at the end of each shaking day. We remember going at EDefense really, really early in the morning, like 3 or 4 a.m. to conduct those. And we are very appreciative to the EDefense counterpartners for accommodating us. So in the next slide, you can see a couple of photos of those scanners that we used. We used mainly the short-range scanners inside the building to capture the different cracks and different deformations inside the building, and the longer-range scanners from the observation decks to capture global response. So I think in the next slide, I start having explaining how we use those. So we perform scans both interiors and exterior, and we post-process those to create point clouds. And we created 3D building models for each scanning to use for damage detection. As few sample results in the next slide, we have that last day, which was 100% Kobe, and that's, I think, building B. You see the distorted column after the last day of testing on the left side, and figure A, you can see the photograph taken by a camera, and at B, you can see a screenshot of the column from the LiDAR point cloud. So we could actually measure how much the distorted column had moved in terms of the angle. Also in the next slide, another type of measurement that we could perform with the point cloud was the damage to the 2 bracing elements. You can see at figures A and C are the photographs, and B and D are what we actually got out of the point cloud. So we could measure out of plane deformation in figure B, and as well as the cracks that we could have in the backlink in figure D of the wood bracing. In the next slide, another type of results and measurements that we could identify was from the 3D models. We could identify crack patterns. And this is the same test day. So you can see here on the right hand of the figures, we have the photographs, and on the left hand, we have actually the point cloud. So you can see that we have identified all the different cracks, and with yellow triangles, you can see the area that fall out, that actually got removed or damaged from the test. And in the next slide, this is from building A. This is from building B, which was less damaged than the last shake table test. And in the next slide, we actually could measure the length of the different cracks and the damaged areas as well. And we have provided all that in the journal paper, the Journal of Structural Engineering, which is in press coming out soon. And that was a collaboration in the publication as well with Professor Nagai. Following up from a test in Japan, we performed an expert panel with US engineers, and we are working towards some performance-based engineering recommendations. In the next slide, I would like to acknowledge from the US side, the US National Science Foundation for providing financial support for the team, Professor Nagai, who has been a great collaborator and great help during our time in Japan, as well as Professor Kajiwara from EDefense, Professor Inouye, and Professor Kawamata, who woke up really early for us to accommodate our measurements in the lab. And last but not least, the NIERI Rapid Facility at the University of Washington for helping us out with the equipment and the measurements. And with that, I will pass it back to Professor Nagai to continue the presentation. Thank you.
はい、ありがとうございます。So, let me talk a little bit more. So, the project was started right after the 2016 Kumamoto earthquake. And the Kumamoto earthquake showed very competitive demands to the 1995 Kobe earthquake. We have to consider such demands around the Tokyo metropolitan. And in this project, we focused on new type wood, residential building structure. Not old one, but new type building. And EDefense has enough, experience on old type buildings. And okay. Full-scale structure foundation soil system were completed for the test. Pipelines are installed to represent important functionality of residential building. And Mr. Yamada designed his reasonable test setup protocol. And in the test, the building showed damage to upper structure, as well as pipelines. And Dr. Kawamata investigated PVC drain pipelines deeply, and he represented such paper. And flexible gas pipeline showed high seismic performance. As well, if you use high specification for drain pipeline, you can enhance PVC pipeline around the joint. Okay, so one important column of this project is CT monitoring system, comprehensive system. So many kinds of sensors are installed in the system, and Dr. Hayashi represented such paper already. So now, seismic performance of residential buildings. JMA Kobe 50% is DBE, apparently, and the index 3 residential building adopted in this test showed good performance given input of DBE with no sliding at foundation. So no sliding at the foundation. And the maximum drift angle was less than 1% at the first story. So quite a high performance in DBE event. On the other hand, in MCE, GMA cover 100%, sliding occurred at foundation. And the maximum drift angle remained at the most 1.5%. So this is very first test in the world, full-scale structure and soil foundation interaction in reality. So you can see the sliding consumed, demand sliding of the system instead of the upper structure. So this is very strong message to us. Again, once we adopt very artificial foundation, a completely fixed foundation, this is artificial again. So you can see completely messed up upper structure without any sliding at foundation. So this is very conventional, traditional testing protocol to find the capacity of upper structure. However, the real boundary condition is soil foundation upper structure system. And this is first story shear force coefficient drift angle hysteresis given base sliding. Once you fix the base completely, you can see very deteriorating IMK model type of hysteretic behavior. So very comprehensible, very comprehensible. So the sliding occurred before the ultimate strength of upper structure, and you can survive like upper hysteretic case. So how we can explain such phenomena in design practice? This is a very high hurdle. So we have to continue enhance our capability for practice to reproduce or represent realistic phenomena, which is quite high impact to behavior. So incremental dynamic response analysis is quite a strong option. Once we secure reasonable parameters, it's quite hard, but once we secure reasonable parameters, we can use this traditional PDEE methodology proposed in 2001 or 2000. The response of upper structure is mitigated statistically given foundation sliding once you incorporate such system into incremental dynamic response analysis. So this is quite affordable option. Next, in the newest Japanese code, capacity spectral method is available, which is not very famous, and also not very popular in practice. You have to understand quite high, how do you say, practical, methodology. But you may incorporate such methodology for the representation of sliding. The left graph base isolation system and wood structure system middle, and the right side soil foundation system. So, high inelastic behavior, but very consistent and consistent to capacity spectrum format. So you may use such format for practice, even for soil foundation system, which is completely ignored in this stage. In near future, we have to try to disseminate, because this is reality. This is a reality. And the base isolation system, that is quite highly produced artificially, so quite how do you say, reproducible. Not just JMA Kobe 100%. JR Takatori 100%, you can find very consistent, format results, including soil foundation system. So this is one more strong option in our country, even in US. According to a rumor, capacity spectrum method is not very popular in United States. I don't know. So in this project, such target is very high according to current practice stage. So at least in this project, we have to continue polishing numerical analysis technology, methodology. And my student is now struggling with such, numerical approach, how do you say, training, period. Thank you very much.
Thank you very much, Nagai-san. For the interest of time, I would suggest to keep the questions at the end, just to make sure that we are right on time.
Okay.
Just observation. We want to make sure that we are not late for that, right? So the next presentation is focused on the Japan-US collaboration on reinforced concrete structure test, and there will be an update on the RC test by Dr. Trevor Yao from Tokyo University.
Yep. Okay, so thank you very much. So as mentioned, my name is Trevor Yao. I'm here to represent Professor Kusunoki Sensei, who's unfortunately busy today with other things, so I'm taking his place. So before I start, just want to acknowledge the works supported by the Tokyo Metropolitan Resilience Project. It did completely slip my mind to acknowledge some of the other people involved. So we got some from Building Research Institute, the companies involved with the sensor installations and providing the sensors. Others from University of Tokyo and University of Hiroshima in terms of the non-structural element aspects. And of course, our colleagues in America. So Professor Palio and Professor Mustafa, who will also present after I'm done speaking here today. So for the interest of time, I'll skip this part since most of us are already familiar with the project. So in terms of this particular test, there were two main backgrounds or objectives associated with it. So the first one was regards to the poor response of buildings that were intended to have post-disaster functionality that was observed in Japan over the last few major events. So for example, on the left, this is a city hall building that was quite significantly damaged in the Kumamoto earthquake. And then on the right, we've got a school gymnasium that was meant to be used for temporary shelter purposes that was damaged in the Tohoku earthquakes. And so to address these issues, there was a new performance objectives that has been proposed recently, where firstly, the base shear coefficient must be at least 0.55, which those of us who designed buildings before knows that that is a very, very strong building. Secondly, under the severe earthquake motion, that's similar to either the ULS or sometimes the design basis earthquake, the peak interstory drift should not exceed 0.33%. Once again, this is a very stringent performance objective. And finally, the members should be mostly elastic under this particular event. And there's also been some guidelines regarding non-structural elements as well. And so to address this issue, one of the solutions that was conceived was to utilize the cladding elements in the structural response, since we need to use cladding elements anyway. So there were two alternate solutions to this. The first is what we call the seismic gap detailing, where we break the cladding elements into 4 sections. So the wing walls, the standing wall, and the hanging walls. And the horizontal wall elements are not connected to the column on the wing walls. And this is to ensure that the plastic hinge location occurs where we intend, and to also minimize damage to the wall elements itself. On the right side, we have what we call the cut reinforcing detailing. So in this case, there is no gap, but the reinforcing does not go all the way through. So the concrete there still acts in compression. So this is one part of the test that we were interested in. The other part was regards to structural health monitoring. And the reason for this is that following major earthquakes, and obviously building inspections would be required. Imagine in a very large metropolitan area like Tokyo, this can be very labor intensive and time consuming. And so we may have people unnecessarily displaced from their homes or businesses for a very long duration, which has very large social economic effects. And sometimes building with hidden damage may collapse during a strong aftershock or subsequent event. And these needs to be identified. And so Professor Kusunoki Sensei proposed a method to estimate sort of the capacity curve of the building based on the acceleration results. And then based on this capacity curve, we can estimate the level of damage in the building. And so based on that, the main objectives of this test was to identify if the structural solutions proposed are able to satisfy the performance objectives, evaluate if the structural health monitoring approach is capable of predicting the building's damage level, and finally is to evaluate if the improved non-structural element detailing results in improved resiliency. There were also other objectives that was covered, particularly from our US colleagues, but they'll discuss it more in their presentations. So let's have a quick look at the test setup. So this is an 80% scaled building, reinforced concrete. You can see some non-structural elements on the photo on the left. So we got tile exteriors on the right-hand side of the bay here, windows on the second and third floors, and also ceilings on that side as well. From the structural part, we have the gap detailing on the second and third floors, and the cut reinforcing detailing at the top floor and the base. So just a bit more photos on that. So when we look at the base, for example, we can see the column reinforcing does penetrate all the way through to the foundation beams, but the wall reinforcing does not. So these sort of act in compression as well. For ceilings, ideally we wanted to test different types on the same floor, but due to space limitations from instrumentation, we can only do it on one bay. So on the third floor, where the acceleration is higher, we have the more resilient option, where we have about a 6 centimeter gap around all the edges and bracing in the ceiling. On the second floor, it's connected on all sides with no bracing. Windows on second and third floors. On the right side, we have the sliding windows. On the left, we have the fixed ones. On the third floor, we have a single panel, and this is expected to fail at a lower drift. Second floor, we split into 2, and the drifts are high on the second floor as well. For the exterior tiles, we use 2 types of adhesive. On the left side is a mortar adhesive, and we can see it's a bit thicker. On the left side is more flexible, so the tile shouldn't fall off during the shaking itself. And finally, we've got some piping on the roof where we tested different types of base connections. With regards to instrumentations, we had laser transducers, displacements, potentiometers, and different types of sensors to check whether the cheaper options are able to give us as accurate results as more expensive ones. Obviously, there are others that were used as well, such as strain gauges, other laser type of measurements to measure drifts, and so on. For the ground motions itself, we use an artificial record where the 100% scale is equivalent to the code design level. And we ran this 5 times using different scale factors to check different performance objectives. This was done over 3 different days, and at the end of each day, we we did a crack check to see how much damage was in the building. Obviously, we can't do it after every single test because stopping and stopping the shake table was very time consuming and also quite expensive as well. So let's briefly look at the test video. So I'm going to jump straight to the 150% one because there wasn't much happening in the 60 and 100. And I believe this one was the one that those of you who were here last year had a look at. So during this particular test, you'll see some cracks occurring between the beam and the wing wall elements on the third floor. And somewhere soon, you'll start to see some tiles falling out. Not too much damage at the column base at the moment, but you can sort of see it starting to lift up a bit, almost like a rocking wall. And once again, that's because we don't have any reinforcements going through to the base in the wing walls. This is the very next one, which is the second run of 150. If you look at the column base, you start to see more response there, and you can also probably see some concrete spalling out the side as well. And we also got some tiles falling out from the third floor in this case. I should mention that for the beams, we are looking at the mortar side. Unfortunately, I don't quite have the videos for the flexible end. But we can see that with the mortar detailing, we are getting quite a bit of tile fallout. And the fun one, which is the 160 events. This test was stopped prematurely because I believe the velocity demands exceeded the shake table capacity very slightly. And so it was stopped prematurely. You can also see some tiles falling out from the base of the column as well, indicating the amount of damage that we are starting to get down there. Key findings from the structural side. This is the cracks that was observed in the third floor beams. We can see after the 100% shake, it's very small crack, so it was considered minor damage. It's starting to get more significant after the first 150, and after the very last shaking, there's been extensive spalling, and the bar has started to buckle a bit, but not too significantly. At the roof level, the beam itself had smaller crack widths, so they tend to perform slightly better there. Unfortunately, though, the hanging wall had quite large cracks in there. But we should remember, though, that we do not have the reinforcing going through those cracks. So this looks bad, but it's not actually that bad from a structural viewpoint. From the column base, we can see some corner crushing occurring after the first 150. And by the 160, there's been quite extensive damage down there. The floor slabs wasn't too bad in the first one, about less than 0.2 as well. But yeah, after the 160, it was kind of getting a bit on the scary side when you're starting to see cracks about 12 millimeters wide. In imperial units, I believe that's about half an inch. Interstory drifts, we can see for the 100% case, it more or less satisfied the 0.33 drift limit. So in other words, this satisfied one of the performance objectives that we had specified earlier on. This here is looking at the residual crack widths, but I'll skip ahead. This is the damage evaluation that was considered based on those drift limits from before. And from what we can see, if we look at just the beam cracks on its own, it's relatively slight or minor damage. On the first floor, it was determined to be moderate, but I believe the R value cutoff was about 80%. So this is about borderline between minor and moderate. So based on this, we judged that the system was more or less in the last having minor damage. For the 150% case, it was starting to get quite significant. And for the 160, we considered it to be close to collapse, so we didn't consider it there. This is looking at the structural health monitoring approach by Kusunoki sensei, where we can see that at 20%, there's almost no damage. At 100%, minor or slight. And also note that it's in an elastic range. So this satisfied yet another performance objective. For the 150% case, it was severe, partially damaged. And by the 160, it was close to collapse. I'll briefly run through this non-structural response. So this here is the ceilings. Both of them performed reasonably well, actually. But what we noticed is that on the second floor, there has been some gaps forming, and the engineers involved in this particular aspect judged that the ceilings was potentially on the verge of failure on the second floor. So this kind of showed that the third floor building, despite the third floor ceilings, despite being subjected to high accelerations, looks to have performed better overall. For windows, there were cracks on both the second and third floors that actually occurred earlier than what was anticipated. So there's still looking into the reasons for that in more detail. Tile response, as we saw in the videos for the mortar adhesive, we can see that the tiles are spot off. However, for the other type, we can see that while a crack is formed through that, the integrity of the tiles is still upheld. So there's limited, less risk of injuries from tile fallout, which is a good thing. So key findings from the structural, from the test itself was that the building did mostly achieve the design performance objectives. The structural health monitoring does agree reasonably well with the damage evaluations, and the improved non-structural element detailing does appear to lead to better seismic performance. And just to briefly wrap up, we did have a blind prediction competition for this particular test, where the motivation was that because there's been the use of structural analysis tools has been on the rise in recent years, it's not very clear how accurate these are for modeling uncommon building types. And because our building is a relatively new solution, it's a great opportunity to evaluate the accuracy of these tools and assumptions. And so what we did was that for the 100% and for the first 150, we asked participants to predict the roof displacement history relative to the base, peak interstory drift on all floors, and peak base shear. And we just used the sum squared error for calculating the error. In order to select winners, we ranked teams based on each individual category. Then we summed up their ranks to obtain the final score, and the teams with the lowest sum score were declared the winners. We announced the competition in September 2019, and everything that the participants required to perform the analyses was uploaded by January of this year. The initial due date was, I believe, early April, but due to COVID, we had to extend it to May, and we announced the results in August. So 16 teams joined in particular, 12 from China, 2 from Japan, 1 from New Zealand, 1 from Greece. Originally, there's meant to be 30 teams. I think it was actually more than that. But obviously, due to COVID, a lot of teams had to pull out, especially because this was held at the time when the first waves were happening global-wide. So this is just a brief look at some of the results that we had. And you can see, for example, Team 5, that their results were actually very, very accurate compared to the test results. So this is all the ranking table that we used to identify the top 4 teams, which in no particular order were Becca from New Zealand, a couple of teams from China, and NTERI Network from Japan. And each of them received a certificate such as the one that you've seen on here. And we've also had a press release through the University of Tokyo summarizing this. We are having part 2 of the competition where we are asking participants to predict the response for the next 2 tests. And what we've done here is we've actually provided the acceleration results for the previous test. So that can be used for model calibration. And one of the motivations was to see whether we can use such results in practice to better estimate the models. The website has been live as of November 17. Unfortunately, hasn't been too much interest so far, but if you can help spread the word, it'd be much appreciated. Just to wrap up, here are some of the publications that we had regarding our testing so far. The ones highlighted are journal papers, and the ones in green have so far been accepted or published, and the ones in yellow are in the process of being reviewed. And finally, we have a special session at the World Conference next year, if that goes ahead. So please join us if you are available. Thank you very much.
Thank you very much, Dr. Riao. The next presentation is on the Japan-US collaboration on the seismic performance of reinforced concrete structures, and I will be from Professor Paolo Calvi from the University of Washington. Or Jeff?
Yeah, actually, it's going to be me. Sorry about the last minute change. We're living through a pandemic. Paulo has 2 small kids and his wife is pregnant, and asked me at about 3 o'clock today if I could do this because some stuff came up. So I'm happy to step in for him. Good evening and good morning, I guess, in Japan. We were all there last year. I wish we could all be there again this year. It's just so much fun to go to the facility and to meet everyone and work together on some really great stuff. These slides were prepared by Paulo and Tatsu Sweet. That is the PhD student working with Paulo and with Laura Lowe's on this project. This was a collaborative proposal that also supported Muhammad Mustafa's work at the University of Nevada, Reno, but we'll talk about what's going on here at UW. So just acknowledging everyone, there's a huge Japanese team, as Trevor mentioned, so we'd like to particularly thank Trevor, Professor Nishitani, leading the whole Tokyo Resilience Project, and then Professor Kuzunuki, who led the concrete tests. Of course, Dr. Nakamura at EDefense was there really late at night with us. So Maria did her work on the wood frame specimen in the morning. We did our work at night, and we're often there until 3 or 4 o'clock in the morning. I don't know. It was really late nights. And then, of course, thanking NSF. So the objective here is to do damage-based post-earthquake assessment of reinforced concrete buildings and to move that entire discipline forward using new technologies similar to what Maria showed. This will be a lot of point clouds derived from LiDAR data. And the idea here is that, of course, we're collecting controlled data and then doing data processing on that. I'll skip real quick through the descriptions of the test because I think you just saw all of that, but it was a fantastic test. So what happened here is we deployed the rapid facilities equipment, largely LiDAR, and collected data from the experiment, which we then turned into point clouds. And we're in the process now of kind of processing that data and developing some methods to extract damage and damage measurements from that data. So like we said, the PI is Paulo, Laura Lowe's is co-PI, there's a graduate student, and then we have also are working closely with Muhammad at Reno as well in his DIC work that you'll hear about next. So again, here's the test specimen. There is us, several of us that made the trip out, and Professor Nakamura probably looking at her watch saying, how late do you guys need to go? We're running one of the laser scanners. So the way this went was we did baseline scans before the first day of testing. And then there were 2 ground motions that were run, 20% of design wave, 100% of the design wave. Then we did another set of scans that night. And then they ran 150% of the design wave. We did another set of scans. And then on day 3, they ran 150% again. And then the 160% that Trevor showed the results for. And then we did another set of scans after that. So what did we use? We used close range laser scanners. I'm not going to go through the details of this, but these are highly portable instruments that we took a whole lot of data with. I will say, so I kind of run the rapid facility along with Joe Wortman. This is generation 2 of our laser scanners. Maria used generation 1, and I think we're able to do a little bit better measurements for crack identification and things like that now with the current equipment that we have. So this is a super fast laser scanner. Takes I don't know, it's millions and millions of points. It's amazingly fast. And then we have a really high resolution scanner. It's the Leica P50 scan station. It's really the highest resolution, highest accuracy scanner, terrestrial scanner that's out there right now. This is what we're, I think, currently recommending people use if they're interested in really capturing subtle details of damage in structural systems. We also brought along a total station to do kind of global measurements. So we collected all this LiDAR data at the instances that we talked about, and then we put the whole thing, all this stuff together into these very rich, detailed point clouds. The point clouds contain XYZ coordinates of each time the laser hits the test specimen, as well as each point is tagged with an intensity and RGB color values. And so there's a richness to this data that's not necessarily available from photographs. For some of the detailed work, we set the P50 up after test 3 in 11 different positions inside and outside the building, and did some very detailed scans with this specimen, and we'll zoom in and look at some of the results of that. But there's a huge number of points that are collected. A lot of it is the facility and things that we don't want anything to do with. So our first job is really to clean all of this out and focus on really just the data that's of interest, which of course is the specimen. The smaller scanner, we did a whole lot of, we did 81 scans after test 3, and the number of points was absurd. The data is a pretty heavy lift here. So the first thing we do is clean everything out. And so this is just kind of illustrating the point cloud, but I want to get to some of the detailed analysis of the damage. So here's a zoom in of one of the cracks forming in the beam. You can see the gap in the spandrel that's detailed. So this is a lower floor where there was provided a seismic gap. And we can see the crack going up into the slab. So that's, some really, I think, detailed measurements. We can see cracks in the reinforced concrete beam elements from the inside and spalling. If we look a little closer, we have really high resolution in these areas. We're getting a really good picture of the damage. We can take some very detailed measurements of these cracks from the scanners, from the point cloud data. So I'll go through how we're doing the crack measurements in a second, but we're also, of course, measuring global deformations with fixed points on the specimen. We had a number of targets that are very useful for comparing kind of before and after shaking. So we do that with when we compare the target location, say in a baseline scan, and the target's just convenient because it's an easy point to locate. The middle of the target is an easy point to locate. But of course, we could use any point within the 3D point cloud model. But we're able to see the difference in deformation between the baseline configuration and then after test 3. And this is, of course, corrected for shake table deformation or shake table displacements. So this is the actual deformation of the specimen, residual deformation after test 3. And then we're doing a few things trying to work on some damage detection stuff. This is relatively new. We're trying to adapt some algorithms that have been used in 2D environments from photos as well. So really very much a work in progress. But we've got some areas where we have very detailed scan data of of damage to this specimen. And so I think it's a really rich data set for those who are interested in doing kind of algorithm development for crack identification and crack measurement from point cloud data. It is a super rich data set that, you know, obviously is available on Design Safe now, and folks can go and start to investigate it with their own methodologies. We've done some really basic stuff in the beginning where we're just fitting surfaces and trying to measure the distance from the surface into the depth of the crack and things like this. We're comparing our crack identifications and kind of our crack mapping from the point cloud to the hand crack maps that were drawn by the Japanese team in the field. Some really interesting things that we've kind of discovered by accident is in this location, we actually scanned the top and the bottom of the slab, and we're actually able to connect the crack all the way through the slab. So we had you know, a few hits of the laser that went really deep into the crack in the slab. And so we're able to look from the top and the bottom and kind of map that crack all the way through the slab, which is really interesting. And like I said, we're in this process of kind of exploring different filters, different methods. We have this, we have the distance measurements, the intensity, and the RGB to work with. And so there's a lot of potential avenues for understanding how to find the cracks and how to map the cracks, how to measure the cracks. And so that's really where we're going at this point. And this just kind of summarizes all of that. I know we're a little bit behind schedule and I don't want to miss the test or don't want us to miss the test. So I will turn it over to Mohammed. I will just add one final little thing and say that we actually did some dynamic measurements with the P50 with our laser scanner. So we set it up on the floor to measure the displacement of this column during the test at a rate of about 50 hertz. And so far that's been really, really successful. So, you know, it's kind of taking all these points, and I'll just skip to the end where we compare it to the Japanese instrumentation data. And so far it looks like the line scan and the displacement data from the Japanese researchers' instrumentation lines up really, really well. And so if you want to make some dynamic measurements with this LiDAR system, I think, you know, it's looking pretty good. And we can do that.
Jeff, I'm really sorry to interrupt you, but we're a few minutes.
I'm done.
So Mohammed, if that's okay with you, we'll proceed with the test observation and we'll come back for the last presentation of the session. Thank you, Julio. So the last presentation of the session is on the digital image correlation system for the test monitoring for the concrete test. And that presentation will be by Professor Mustafa from the University of Nevada, Reno. Floor is yours.
Thanks, Maria, and thanks everyone. Just you can see my screen, I guess. Let me put it in a full screen mode. So thanks everyone for the opportunity to give you an update today and share with you like some of the work that we've been doing as part of this like nice collaboration, not only with like our great, you know, like Japanese friends that we got, you know, like to work with like over the last year, but also with like our friends here in the US from University of Washington. So that has been like a nice collaboration so far. So our aspect, like I'm not going to repeat, you know, many of the aspects that you have heard about already from the previous two presentations. So our focus was, you know, like on the using vision-based system with the concept of digital image correlation to get the seismic response, you know, like and structural health monitoring basically of the structure. So I had like Luna, a postdoc working with me on this. You know, like she was a PhD student when we worked on this project, but now she, you know, like is a postdoc. And of course, you know, like I would like to acknowledge NSF for this, you know, like grant. There is a lot of acknowledgements, but for the interest of time, I know that I'm just between you and the break now, so let me get brief here. So vision-based monitoring in general, you know, like there are different types of vision-based monitoring. One of them are like different concepts, basically, like, you know, starting from all the way, you know, from computer science, computer vision, different algorithms to other optical, you know, like sensors. So there are different techniques, you know, like the underlying algorithm that we are using here is basically digital image correlation with application for target tracking, basically. So digital image correlation like is pretty like old, you know, like concept and has been used for like strain mapping and crack, like mapping and strain like measurements. As like this is actually was the first time I was introduced to this technology back at Berkeley during my PhD. But like this is technology is like well established, I would say, and there are more emerging like ways of using digital image correlation to do like target tracking. So that's an example here on the right hand side for like the target, or like now like there is also target list, which is using like natural feature detection and things like that for creating like virtual targets that could be tracked as well to get like a static and dynamic response. So what we are doing like at our for those of you who are familiar with like our shake table test facility at UNR, like we have this multi-shake table test facility and we do a lot of bridge testing here. So this was the first time we tried like to deploy our system here, and the system basically is like a pair of camera. If we are like interested in getting like 3D deformation, we have like a whole bunch of lighting like that we shine on the targets, the black targets that you can see here. That's what basically each one of them become like a sensor, and we get like XYZ like coordinates in from a dynamic response, like during a shake table test, or like even under ambient excitation to do like structural health monitoring and things like that. So we tried the technology like for the past few years at UNR, and it worked fine. Then we were presented with the opportunity to be part of the team to monitor this at EDefense. So we worked with the University of Washington, and like we collectively from the US, we had a team. They focused on the damage detection, as Jeff like explained in nice details, and you have seen all these great pictures that they showed. We like on the other side were like focused on the dynamic response monitoring, and we deployed two systems for like for this like I would say like a state-of-the-art type of like camera. These are like $37 like pair of cameras, like high speed, high like range cameras, and specialized, and also commercial cameras. So we can $500 type of cameras, and we wanted like to cover a wide range of like camera like hardware or basic hardware capability, and see if we can get like the systems to work. These are the targets that we used. And so this is the side of the building that we ended up monitoring from a platform that was, I think, 30 meters away from the building or something like that. And like this is a close-up of some of the targets that we used. You can see here we do use two different types of targets: coded targets, which we use for calibration purpose, the ones that look like more larger ones, and they have like more rings outside, like the center, and then these smaller targets, which like we use as many of them for getting the dynamic response during the tests. So the thing is that like during this, every monitoring setup has its own challenges. Like you never know like if the monitoring would work or not unless you set up the like the setting of the cameras. It depends on the ambient lighting condition, and most of the time we need additional lighting. For this special project, like there wasn't an opportunity to like shine extra lights on the specimens, just because like there was like a lot of like sensors used inside the building. A lot of them were laser-based sensors, as like you have heard from Trevor like half an hour ago or so. So because of this, we're not able to shine any additional light. So that what you see here basically is not what the camera see. When you adjust like the shutter speed and the focus of the camera based on the dimension, the field of view, what you'd like to capture, the camera would see an entirely different thing. And this was the biggest challenge that like we faced in this project, which it was a great challenge because it led to a side research project on the side. So that's like what we can see. What you see here in the left-hand side, that what we could see from the high-end cameras, the high-speed cameras, and like none of the targets basically were identified. And from the Canon cameras, which even has like more like relaxed settings and can accommodate more like challenging settings, even this Canon cameras, or like 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 basically the more relaxed setting, was not able to capture like most of the targets. And what we ended up is like a failed calibration file. So we like consider this as a challenge. Actually, we didn't consider this as a failure. And what we wanted to do is just to see what we can do to get like to enhance these like types of pictures for like still getting all the results that we intended to get. So we went back like after we came back from Japan, we went back to our lab and we tried to devise like a framework basically for image enhancement. And we didn't want only to do image enhancement, but we wanted to quantify the accuracy of this like image enhancement procedure that we like developed, and quantify the measurement. So we went to our lab and we deliberately like made a whole range of like dark images. And like this is, for example, like I'm just showing a small example here. This is how we can like get down to the pixel level type of gray distribution of each pixel in the picture, how we can apply some image enhancement algorithm so that we can redistribute like the the grade distribution basically of the pixels. So we are doing basically like an informed type of image enhancement that is targeted so that, like we can get a specific distribution of the black and white and gray distribution within an image so that it can be registered when we do the post-processing for, like calibration, and eventually get successful targets that can all work as sensors as intended. So we tried this in our lab. We did like a whole bunch of static and dynamic tests to verify, like the accuracy of the algorithms. Once we had confidence, in this, we applied it to the all the pictures that we got from the Japanese test, and it was a great success. So that's what I'm proud of, is that, like we're able to get like a side research study, as I said, as part of this project. So that's the original image as we captured it from the, based on the setting in Japan. Like this is after image enhancement, and you can see we were able to get every single target, we had coded and uncoded from the high-end cameras and from the commercial cameras as well. So that's another example here from the like lower end type of cameras, and also with the image enhancement, we were able to get all the targets. So this, we just tried to wrote a paper actually out of this procedure that we tried to develop here and quantify using the EDefense test as a test bed. So this is work in progress. But now that we have, we are completely done with the image enhancement, and we know now that we can get the right data. It's all about, generating these data. So very shortly, we'll also be working with University of Washington and our Japanese, collaborators to see how we can share this data and compare them, because there are a lot of things that we can compare here. And I will show you some examples next. So the first thing, we have in this type of tests, and typical shake table test, and probably have heard about this from Trevor as well. We use ambient, or excitation or white noise tests, and we do these to do system identification and get to do structural health monitoring basically for our structure. So I'm just showing a sample here. Every target, remember that every target we have here, every one of these black stickers that you see becomes like an accelerometer, if you will. We get, acceleration, velocities, and displacements with very, good accuracy, because we have been working on the accuracy quantification for these, technologies. And we were able to show that, we can get accuracies compared to mechanical sensors within 2 to 3%, sometimes even less than 2% error. So we have confidence on the data, and we wanted to use it now for structural response assessment. So I'm just showing sample here of what we can do with this data. So from the white noise tests, before even starting any seismic shaking, that's the first one. So we can do a full system identification for the building using acceleration data we captured from, our systems. And we were able to, capture the first 3 modes in each direction, transverse, longitudinal, and vertical direction. And we continue to do this actually between the seismic tests as well. So that's one way of doing structural health monitoring, is just to, and that's, I think, one of the objectives of this project that Trevor, presented, is that when it's sometimes the damage is hidden, one way to tell, if the structural health is still in a good shape or not, maybe after a seismic event, if there is under any ambient vibration or any small, scale excitation, we can do a second set of structural system identification and just see the period, or the frequency shifts, softening when it happens, with the loss of the stiffness, you get change in the period, and, with a decent system identification method, you can capture this. So that's one thing we are doing. I'm just showing sample here from the results that we got from the original building before any testing. But what we are currently working on is that we'll do this between all the 5 or 6 seismic tests. So that's one type of data we were able to get. And this is one type of post-processing for the data that we got, how we can use this data to, assess the structural response of the building. The second thing is that we are getting displacements, and we are focusing more on displacements here. So I'm showing some sample, for the next few slides, I'll just share with you some samples here. We're not done with all the post-processing yet, but I can show you some of the samples of the results that we are getting. So here, what you see in blue and red, we are comparing the two systems, our two systems, the lower end cameras and the higher end cameras after the image enhancement and everything, of course. And we were able to show, actually, for the first time, I don't think anyone has seen shown this before in a large scale test like this, that a $500 camera can work as well as a $15,000 camera. So the hardware itself, we were able to show how to use more feasible, hardware for monitoring applications like this. So these are the total displacements that we got for the building at the different points. I'm just showing some samples here. This is total displacement. You need to just subtract from it the input motion or the input displacement. You can get the relative displacements, and we can get interstory drifts, which I'm showing some samples also in following slides here. Another aspect of this project is the seismic gap that you heard about again from the previous presentation. So it's part of the structural system. So we thought about, like having, like targets at each of these gaps that we can capture in our system, and we were able to get the relative displacement within the gap itself, which we could translate into rotations and get maybe a better idea if this gap is helping or not. So we haven't again post-processed the data from a structural perspective yet, and this is something to do in collaboration with our Japanese collaborators. So of course they are the ones that put together this structural system, and they are the ones that know what type of response they need to assess here. So we will be working with them, but at least we were able to get this type of data, so we could get the relative opening and closing of the gap during the test at the various tests. Another thing we were able to actually, that's another example here. So the 150 test, 130% test with 2 runs were done from this, run 5 and run number 6. So that's some more examples from the second test. And that's another, let alone now the total displacement that we were able to get. We also have some of the targets on the shake tables here. So we were able to get the table input displacement, and we were able to calculate, the relative displacement at each floor and the interstory drift and the interstory drift ratios. So what you can see here, is the interstory drift ratios. Again, how would we use something like this? There is a performance assessment criteria, which Trevor has shown, 2%, for example, interstory drift ratio, or 3%, I don't know, the limits. We yet to use the right limits for the assessment, but at least we were able to get this. And the second floor showed a higher interstory drift ratios relative to the third one, which is the same thing that you have seen in a previous presentation from Trevor as well. So that's another sample of the results that we were able to get, the interstory drifts and interstory drift ratios. The gap relative displacement, these are more examples here. So we have actually 4 gaps, and we were able to capture the relative displacement of all the 4 gaps, just to give you a sense of the results. Each of these gaps, we're seeing almost up to 2 centimeters or 20 millimeters of relative, displacement closing and opening during the seismic event. So we yet to translate this into rotation and try to tie this to the structural performance of the frame. And one last thing here also that I'd like to share with you is that this was a 3D system. Although this was a uniaxial motion, but yet since we are using a 3D system, we were able also to capture the out-of-plane response. So I'm just showing some example here of the out-of-plane response. It is minor relative to the in-plane or the intended, motion, but we were able to still capture the out-of-plane, resulting vibration that happened. If we were to, compare these relatively, so if we were to subtract, results from these 2 points, we could get also some idea about if any bulging is happening in the wall. So these are all some of the ideas that we could do in terms of the post-processing and assessment of the structural and non-structural component. But so our focus now in terms of the timeline, over the next 2 or 3 weeks, the data set will be available. We're not sure if it will be published right away, but we're working on this. So we'll have the data set fully, all these targets that you see here, every black dot, we will get, XYZ for all the tests. So we'll have the full displacement and acceleration data from all these targets. And then the next step is that we are working with University of Washington to compare, you have seen Jeff showing the line scan at the end. So we'll try to compare the line scan and see if we can use our system as maybe a way to verify further, the line scan at more data points. Of course, we will work closely with our Japanese collaborators to see if there is, some interesting comparisons we can do between the accelerations that we have gotten from the vision-based sensors, the displacements, and these type of things, of course, will be put into a structural assessment framework as well. So here I was not wearing my concrete hat yet, but I'm a concrete person, so I would love also to wear my concrete hat and go and see how this reinforced concrete structure perform under the different earthquake levels. So using these data will enable us. So we got actually a wealth of data from this vision-based system that we can complement what you have seen from the UW team and from the all the sensors that the Japanese deployed and will be also kindly sharing with us at some point. So that's what I wanted to share with you today, and I would like to thank you all again for the opportunity, and I will be happy to answer questions if there is any.
Thank you very much, Mohammed, for the presentation. I guess we could take one question for any of the presentations of the session from the audience. Okay, I guess no questions. I know there is a break on schedule. I'm not sure, Julio, if you want to proceed with the break or with the next session.
I think that in the interest of time in the East Coast and also for our colleagues in Japan, maybe we will just continue to the next session. If that is an agreement, is that okay with you, Dr. Kajiwara and Professor Nishitani? Any objections? So I think that we can move to the next session then.
Okay.
So thank you very much, Maria. It's it's amazing even in a two-dimensional format here and on the screen to see the capabilities of this fantastic facility and what researchers can do there. I wanted to comment on all this data that is being generated from these collaborations at the appropriate time agreed by the collaborators. It will be made available via DesignSafe for those projects funded by NSF and then available to the community for reuse and generate new knowledge. So this is like the gift that keeps on giving. Thank you, Maria. Let me, before we go to the next session, I would like to invite Dr. Pauschke to say a few words. We have some guests from NSF that she would like to introduce. Dr. Pauschke?
Thank you, Julio. I'd like to just introduce two of my colleagues at NSF. The three of us work together in the Engineering for Civil Infrastructure Research Program, and it's the Engineering for Civil Infrastructure Program that funds the research that's utilizing the EDefense seg table. So I'm just going to ask each of them to introduce themselves. I start with Giovanna Biscontin.
Hello, everyone. My name is Giovanna Biscontin. I am a geotechnical engineer. So within the ECI program, I look after the projects that involve soils and potentially coastal infrastructure. I was an academic at the University of Cambridge in the UK, and I was in Japan earlier this year from January through March, and seeing those little wooden houses being shaken made me think about my neighborhood in Kyoto, and I was a bit homesick. So I hope that we'll be able to travel again and I can come and visit EDefense one day and be able to see the fantastic marvel that center and that facility is. Thank you very much for all the interesting presentation, and I'm looking forward to more interactions with all of you.
Okay, thank you, Giovanna. And Chalar Aske, would you like to introduce yourself?
Sure, thanks, Joy. Hi, everybody. My name is Chalar Aske. I am the third leg of the Engineering for Civil Infrastructure program. I am primarily responsible for the materials, non-hazard structures, and construction engineering aspects of the Engineering for Civil Infrastructure portfolio. My background is more on computational mechanics. I am a rotator program director. I am coming from Vanderbilt University, and I've been here at NSF for about a little over a year.
Okay, thank you, Chalar and Giovanna. And I just want to say then, sort of as the third program director in ECI, I handle all the structures hazards related proposals and awards. So that's why you see a lot of the projects that are testing here, I have funded. So, and I just want to say to everybody who's been presenting today, the presentations have been fantastic, and it's just really a privilege to be here and listen to all this great research that's being conducted by both the US and Japanese sides in collaboration. So thank you all, and it was fantastic to watch that test. So thank you. So Julio, I'll turn it back over to you.
Thank you, Joy and Giovanna and Shagler for joining us today.